We can move to the wall boundary conditions. So we need to understand what these are first, so we can check. You can see that there are two walls here, and we can plot, for example, the first one here to check what this is. So this is that no-slip wall over here. So we need to set that as a no-slip wall, which is already by default done in Fluent. So we don't need to change that boundary condition. Then we can check what is this one. And you can see that there is like a very small wall section here, which is for some reason detached by the wall, but this is still a wall, a no-slip wall, so that's fine. And then there is the wall slip, which is the one at the top that we want to set as a slip wall. So in order to do that, we go here, we hit wall slip, and we edit it. In order to set a slip wall, we need to change the shear condition. So we need to specify that that wall is not applying any shear stress to the fluid. So instead of no slip, we select specified shear, and we set the shear stress components to 0 in both X and Y component. And we apply it. Okay, so the case is ready. We can keep this, so the numerical scheme by default, we don't need to change this, as well as the controls, we don't need to change this as well. What we need to change is the residuals. So we can go in monitors, residual, and we can set these to lower values, let's say 10 to the power minus 5. So that we are sure that the solution is converged. And okay. Okay, now we are ready to run the simulation, I guess. So we can first initialize the case. We can use this hybrid initialization. And when we use this hybrid initialization, we can already, for example, plot just to check what's happening here, since we have a compressible flow, so a Mach number of 0.5. So for example, I plot the contours of the Mach number for all surfaces. And this is the hybrid initialization. So what the hybrid initialization is doing. So you can see that it's already setting a velocity, so an accelerating fluid as the cross section is reducing, so the fluid is accelerating. But let's now run the calculation. So we can use an automatic time step. I found that we can change the time scale factor by a lot. I tried 10 and it worked very well. So probably how Fluent was calculating the time step was a little bit too much conservative. So we can increase that by 10. And we can run, let's say, for 1,000 iterations, will be more than fine. So we can then calculate. The number. That's fine. that's fine. Because I will show you why that's 525. There is like one small section close to the ball that is like accelerated more than the free stream jet. Were you all able to set the case and run? Okay, so my solution is converged in 88 88 iterations. Let's wait if you are running or. So what we need to check once we get that the solution is that the solution is correct. So we got what we expect. First of all, you can plot the contour of the Mach number. And this is what I get. So you can see that the air is accelerated in nozzle and then is diffused. So there is like a